Okay, good morning. Today is the next chapter, which is chapter 8, which is entitled Chemical Bonding 1. Okay, so we'll start working on that today. I do recommend that you allot enough time to do work on chapter 9. I know we're getting close to the end. We really have, well, actually we have about a week and a half to go before the end of the semester. Chapter 9 is not a requirement, it's extra credit. I will start lecturing on chapter 9 probably at the end of next week. It's not many topics. I think it's around 8 or 10 topics for some extra credit. But chemical bonding 2 is important for those of you that are going to take more chemistry. So if you're going to move on and do, more advanced degrees, the bonding could be very helpful. If you're going to take organic chemistry, 31, 32, you definitely want to work on the bonding. Okay. So, but we're going to do chapter 8. We'll start with that today, chemical bonding 1. And it is predicated on all of that work that we did in chapter 6. Okay, so chapter 6 was all about these orbitals, right? Like these waves. The electrons are waves. And so what has happened is people have started thinking, okay, well, if electrons are waves and they occupy these orbitals, how do we describe chemical bonding from the perspective of these orbitals? And so that's what we're going to get into in chapter 8. It's really cool. Let me start by reminding us a little bit about these orbitals. So essentially, remember, these are called atomic orbitals. And sometimes people call them AOs, right? Atomic orbitals, AOs. There we go. Okay. And remember, we said that you have different types of atomic orbitals, right? So we said you have these s orbitals. So the nucleus is at the center. The wave is vibrating around the nucleus. The lowest energy orbital is the 1s orbital. It's spherical. And then you get another orbital, which is bigger, which is called the 2s. And I'm not drawing that real well, am I? The 2s is bigger. Here, I'll draw the nucleus first and then draw the orbital around it, okay? Remember, these are probability distributions. So there's a probability that the electron is occupying that region of space. And you can have up to 2 electrons in an orbital, right? And then we said, well, but wait a minute, this is the case where n is equal to 1 and the angular momentum number L is equal to 0 and the magnetic quantum number is equal to 0, right? Because it's plus or minus L. And if L is 0, M sub L's got to be 0. And then M sub S has 2 possibilities, right? It could be plus a half or minus a half. And those 4 quantum numbers will determine, really think of it sort of like an address. The first 3 are telling you where the electron is. 1, 0, 0 means that the electron is in this little region of space that looks like a sphere. And then 2s means that n is equal to 2 and L is equal to 0, right? And s orbital is L equals 0. And then M sub L is also equal to 0. And then M sub S could be either plus or minus a half, right? One or the other. And then you get up to the next type of orbital, which has a slightly different shape, right? It has 2 lobes. So it could look like this. So it's a different type of vibration. It's symmetric. I'm not drawing it very symmetric here. There's the nucleus at the center. And people draw these differently. Sometimes they're more bulgy. Sometimes they're, more pointy. I'm actually maybe drawing them a little too pointy. So let me try it again. As you can see, I'm not much of an artist. So maybe like that. There's the nucleus. And it's kind of an odd vibration, right? It's a vibration that has 2 regions. So that's your 2p, and maybe we'll call this 2px. And so that means that n is equal to 2, and L is equal to 1 now, right? That's a p orbital. So p orbitals to L is equal to 1. And that means that M sub L could be either -1 or 0 or plus 1. And then m sub s is, again, either plus or minus a half. So the m sub s is really all about the electron. It's not really about the orbital. It's an intrinsic property. It's an inherent property of the electron, okay? But then you could have a 2py, right? So you could have this. You could say, hey, wait a minute, maybe this orbital actually points in this direction. And so again, there's your 2p. And we'll call this a y. You know, it's a different direction. So n equals 2, L equals 1, right? 2p, 2, 1. But then m sub L is going to be, it's going to be different than it is here, right? You know, like if the first one, and then of course m sub s is plus or minus half, one or the other. If this one's minus 1, then this one can't be minus 1, right? It's pointing in a different direction. So maybe this one's minus 1 here, and this one is 0 here. It's arbitrary which one we call minus 1, because it's arbitrary whether this is x, this is y, and this is z. Maybe this is z, and this is x, and this is y. You know, that's arbitrary. And then you have a third dimension, which I can't really draw very well. It's coming out of the board and going into the board. We'll get into geometries a little bit later. So I'm cutting that one off because I ran out of space. Okay. And so maybe this is 2pz, right? Different direction. N equals 2, L equals 1, m sub L. And then again, if this is minus 1 and this is 0, then probably what's happening is this one here is plus 1, right? It's got to have a different value. And then m sub s, again, is either plus or minus a half. Okay, so those are our atomic orbitals, and those are what are used for chemical bonding. It's going to be, that's you know, an important aspect of it. When we get into more into detail into chemical bonding, we'll say, hey, it's these orbitals that are responsible for the bonding that we're looking at. Okay, so that's you know, really, quite frankly, that's a review of chapter 6. But those atomic orbitals are important. Now, what we want to do is, we want to start talking about chemical bonding. And again, this is chapter 8. So broadly speaking, there are different types of bonding in nature. So one type of bonding that we are actually maybe most familiar with so far in this course is ionic bonding, right? That's something we talked about in chapter 4, you know, the solubility guidelines and the properties of acids and bases, the hydronium ion and the hydroxide ion. You know, we're talking about ionic bonding there. So to talk about ionic bonding, let me come up here onto the web. And a picture is sometimes worth 1,000 words, right? Here we go. Let's just get this picture up here. Are you serious? There we go. Okay, it actually worked. Okay, here is a representation of sodium chloride, which is an ionic compound and involves ionic bonding. So essentially, when we talk about ionic bonding, we're talking about the attraction of ions for each other. So in this slide, in this diagram, this picture, we'll call it a cartoon. On the left is showing you how these ions are formed. So at the top, you have a neutral sodium atom with 11 protons and 11 electrons. It loses an electron somehow, a redox reaction, thereby forming a sodium ion with only 10 electrons. Then at the bottom is it's a neutral chlorine atom, Cl. You can't really see it here because they've cut it off. So this green one down here is chlorine. So chlorine has 17 protons, 17 electrons. It gains an electron, so maybe it gains the electron from the sodium. And now you have 17 protons and 18 electrons, so it has more electrons than protons, so it's negatively charged, so now it's a chloride ion, right? So you have a sodium cation and a chloride anion. What happens is they're attracted to each other, okay? And so they form a little bond between each other, just purely what we call electrostatic attraction. They're just attracted to each other because they have opposite charges. And then what happens is they will fill a geometric shape. They will essentially collect each other in such a way to maximize the attraction of sodium ions for chloride ions and minimize the repulsion of the sodium ions from each other and the chloride ions from each other. Now, there is some repulsion. So these two sodium ions are pretty close to each other, the ones in purple here. So they're repelling each other, but the sodium ion is attracted to all these chloride ions. In fact, each ion, except the ones on the surface, have 6 opposite charges around them. So actually, if you think about it this way, it's analogous to what we were talking about with the d orbital. If you imagine this ion here being a sodium ion in the center, okay, it has, it's hard for you to see this, it has 6, you know, it's a geometric shape, right? This is called a octahedral arrangement. There's 6 ions of opposite charge around it, and they're all attracted to that ion. So each ion has 6 opposite charges around it, except the ones on the surface, right? The ones on the surface, they're limited, right? Because they don't have anything coming out towards you or going above over here. So they have fewer. And so that's why the ones on the surface are more reactive. They're more reactive because they're not surrounded completely by the opposite charge. Okay, so that's an ionic compound, and it's a relatively simple phenomenon. I mean, you can make it more difficult by considering certain aspects of it, but it's really a type of bond that involves generally metals, right? Because metals form cations, and non-metals, which form anions, and those 2 ions are attracted to each other through electrostatic attraction. Now, we can show through electron configurations that ions are stable. And this will be an important aspect of what we do in this chapter. It's called the Octet Rule. So the Octet Rule is based on the idea that certain arrangements of electrons, certain configurations are stable. So we only did configurations yesterday, so this is still pretty fresh in your mind. You may not have mastered it yet. But here's the idea. Imagine I take a sodium atom, Na, and that has 11 electrons. So I'm going to write out the electron configuration for it horizontally. Okay, I'm just doing that from memory, right? You'd have to kind of go through the whole process like we talked about yesterday. So 11 electrons, right? 1s2, 2s2, 2p6, 3s1. So notice you have electrons in the first shell. This is the n=1 shell. You have electrons in the second shell, n=2. And then you have 1 electron. Remember, the superscript is the number of electrons. So in that third shell, shell number 3, there's only 1 electron, okay? What happens is if you lose an electron, we're just going to take off 1 electron. The one that gets lost is the one furthest from the nucleus, okay? Why is that? Well, I guess in theory, it would be easier to remove Pluto from the solar system than it would be to remove the Earth. The Earth is closer to the sun, so the gravitational attraction is a lot stronger than that of Pluto for the sun. So the further away an electron is from the nucleus, the weaker the attraction of that electron for the nucleus, so the easier it is to remove. So it turns out another atom might actually be able to pluck that electron right off. And that would be oxidation, right? If you lose electrons, that's oxidation. And so what you would get is a sodium ion, right? It would be Na+. And if we lose the outermost electron, you get this, right? You've lost this outermost electron. Now, it turns out that this electron configuration is exactly the same electron configuration as neon. And so I'm going to write it like this. I'm going to use another, this is bracket notation. We use bracket notation in different contexts. In this context, the bracket notation means electron configuration. So what we're saying is, if you remove one electron from a sodium atom, you get a sodium ion, and that has the same electron configuration as neon. And it turns out that is a very stable electron configuration. Okay? So when an atom loses electrons and ends up with the same electron configuration as a noble gas, right? Neon's a noble gas, you end up with a stable configuration. And that is a manifestation of what we call the octet rule. Why octet? Because if you look at the second shell, there's 8 electrons in it, right? So the outermost shell now has 8 electrons. We call the outermost shell the valence shell. And we call the inner shells, so that would be like right here, right? N equals 1. That would be called core shell. Sometimes people call it kernel, K-E-R-N-E-L, like popcorn kernel, or it's the core shell, okay? And you can have more than one core shell. So for example, in the sodium atom, these are the core shells, right? And then the outermost shell, how do you tell the core shell? You just look for the outermost shell. The outermost one is the third shell, so the other ones are the inner shells, okay? Core shells. And then, but in the sodium ion, you know, this is the inner shell, and then now this is the outer shell. So core, valence. And notice the valence shell is filled, okay? So there's an aspect of that as well. So let's try another one. This time what I'm going to do is I'm going to take the chlorine atom. Chlorine has 17 electrons, okay? So it's 1s2, 2s2, 2p6, 3s2, 3p5. Again, I'm just doing this from memory. I know these configurations up to some number. I don't know how far I know, but you're going to need to kind of go through it and figure that out, right? So if you take a look at this, the inner shells are 1 and 2, right? And then the outer shell is 3. So this would be called the valence shell. And this would be called the core shells. Okay? Now, notice if you add one more electron. So I'm going to add an electron. I'm not going to remove one. I'm going to add an electron. 1 electron. Just like you lose the outermost, you gain the outermost. So if you put one more in, it's going to go into the outermost subshell. So this is the outermost subshell. So what you'll get is 1s2, 2s2, 2p6, 3s2, 3p6. And that is the same configuration as argon, element number 18. Okay? So we would say that the chloride ion, right, Cl minus, has the same electron configuration. Let me be precise about this. The same electron configuration as the argon atom. And the argon atom is a noble gas, which is pretty unreactive. There seems to be some stability in that, okay? So attaining a noble gas configuration is another way of, it's a manifestation of the octet rule that we talk about. Why octet again? Because now the outermost shell has 8 electrons. The valence shell has 8 electrons, whereas in chlorine, the valence shell has 7 electrons, right? Add 1, you got 8. So now we have a readily available explanation for some of the patterns that we observe in the periodic table. So remember the patterns we saw, which was lithium, sodium, potassium, rubidium, and cesium. That's group 1A. they tend to form charges of +1 ions, right? Well, why +1? By losing an electron, they attain a noble gas configuration. So for example, lithium plus has only 2 electrons, which is 1s2, which is the same as helium, isoelectronic, the same electron configuration as helium. Group 2A, they tend to form +2 ions, cations, right? Beryllium +2, magnesium +2, calcium +2, strontium +2, and barium +2. You can go further. You can do francium. Francium is radioactive. It's unstable. There's it's so unstable, so radioactive that you're not going to actually see it. But we know that it does the same thing if it existed for long enough. And then radium. Radium is more stable than francium, but it's also radioactive. Radium. Okay. So by losing 2 electrons, they will have the same electron configuration as the noble gas that comes before them. So let's put those noble gases. Let's put them over here. Okay. You got helium. Helium's actually in the first column, right? And then, oops, sorry. Then you get neon, and then you get argon, and then you get krypton, and then you get xenon, and then you get radon. Okay, so what happens is if you take sodium, I just did sodium earlier, it has 11 electrons. If you remove 1 electron, it now has 10. So that's the same as neon. Neon 1s2, 2s2, 2p6. So we would say sodium ion is isoelectronic with neon, right? So that's group 1, group 2. Oh, shoot, I'm sorry. I think I may have, oh, okay, it's still there. So then you get to group 7A. 7A is, fluorine, chlorine, bromine, and iodine. There's astatine as well. We don't worry about that. And then 6A is oxygen, sulfur, selenium, and tellurium. So what happens is in group 7A, if you gain 1 electron, you have 1 extra electron, so you become isoelectronic, same electron configuration as neon, right, as the noble gas. So these ones tend to gain an electron. Now I write -1 because that's their charge, right? To become -1, you have to gain an electron. These ones tend to gain 2 electrons to become stable. And you can extend it a little bit. 5A is nitrogen, phosphorus, and arsenic. So they can gain 3 electrons. And some people will even go a little bit further and they'll say, hey, you got carbon, right? Carbon can gain 4 electrons. I've never seen carbon with 4 extra, C-4, I've never seen it, but in theory it can happen, okay? So those elements that we've talked about previously, those patterns can be described in terms of this octet rule, the tendency of atoms to gain or lose electrons, right? These ones are losing so that they become isoelectronic with the noble gas that comes before them. And these ones tend to gain electrons in order to become isoelectronic with the noble gases that are right after them, okay? Very powerful tool, and that's something that comes out of these electron configurations that we talked about in chapter 6. So remember, the valence electrons are the outermost electrons. The core electrons are the inner ones. And the valence electrons are what we're going to deal with next. Okay, that's our next topic. I keep hitting that button. There we go. So let's talk about valence electrons. Okay, there is a pattern that it works out. The valence electrons are the electrons in the outermost shell. So the way you tell is you do the electron configuration and then pick all the electrons that have the highest value of n. So these are the electrons in the configuration, right? So you have to do the configuration first, that have the highest value of N. Okay? So for example, let's do potassium. Potassium is element 19. 19 electrons. So 1s, 2s, 2p, 3s, 3p, 4s. I'm going to stop at 4s because I know how many electrons it has. S can go up to 2, P can go up to 6. Then you count up. That's 18. I've just done 18 electrons. So I got one more. S can go up to 2, right? So 1 is perfectly fine. So there's your configuration. The valence electrons would be right here. That's the highest value of N. So 1 valence electron. Okay. Now, why are we so concerned about valence electrons? Well, valence electrons are the ones that are gained or lost because they're farthest from the nucleus. So the electron goes into valence shell, comes out of valence shell. It's much more, we call labile. They can come in and out. These electrons here tend to be so tightly held by the nucleus, it's hard to get rid of them. Very difficult to get rid of them. So these are tightly held by nucleus. Right? It's all about positive, negative, right? The closer the negative is to the positive, the harder it is to remove it. So the valence shell is where all the action is. So all the chemical bonding is going to be in the valence shell. Okay? Let's do another one. Let's try a non-metal, okay? I'm going to do sulfur. Actually, let's do selenium. Selenium is 34. Element 34, right? So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Okay, you check that, right? I might have made a mistake on it. Let's check it. Should add up to 34 electrons, right? So you add the superscripts, 2, 4, 10, 12, 18, that's a 6, 20, 30, 34. So we got 34 electrons. Then we have to check the order of the orbitals. Remember the order of the orbitals? 1s, 2s, 3s, oh shoot, sorry, 4s, 5s, 2p, 3p, 4p, 3d, 4d, 4f, right? You can keep filling these out. So you do 1s, so 1s, 2s, 2p, 3s, 2p, 3s, 3p, 4s, 3p, 4s, 3d, 4p, 3d, 4p. So it looks like I got the order right. That's all you got to do, right? You got to get the order right and then the correct number of electrons. So there you go. So now what do? We now looked for the highest value of N, and it shows up in two places. It's right here, right? 4. So that's your valence shell. So notice the valence shell is kind of split up. So sometimes actually what some people, when they do these configurations, they'll do is they'll put 3p6, 3d10, and then 4s2 and 4p4. But let's keep to the format of this, of the way we're doing it here, okay? So how many electrons is that? 2 and 4. So we have 6 valence electrons. So to get up to 8, how many electrons does this element need to add? It's got 6 valence electrons. To get up to 8, it would need 2 more. And then you can ask, well, where would those 2 go? Well, this one's not filled, so they're going to go into there. So it turns out the selenide, this is selenium, the selenide ion, anion, might be something like this, right? Se-2. You add 2 electrons and it becomes an anion with a charge of -2. And that would be isoelectronic with krypton. Krypton is element number 36, right? So, you know, this is isoelectronic with the krypton atom, okay? Doesn't mean it's the same thing as a krypton atom. It just means it has the same number of electrons, same arrangement of electrons. They would have different nuclei. The krypton atom has 36 protons, but the selenium atom still only has 34 protons. So they're not the same, but in terms of, there's just certain arrangements, right? If you think about it in nature, there's certain arrangements that are kind of naturally stable. So if you were like stacking oranges, you would realize, oh, make rows and then put the other oranges, the next layer sort of in between where all the other oranges meet, and that's kind of stable. Same thing with these electrons. They kind of fill into these orbitals in stable arrangements. And these noble gas configurations kind of meet all the criteria for being relatively stable. Okay. Now, here's what happens when you start looking at patterns. What you end up noticing is that even though every element has its unique number of electrons, right? Hydrogen has 1 electron, lithium has 3, sodium has 11, potassium has 19, rubidium has 35, and cesium has 55. I'm sorry, rubidium is 37. And then cesium has 55. They all have their own number of electrons, but it turns out they all have the same number of valence electrons. They all have 1. How do I know that? Well, hydrogen is 1s1, so the outermost electrons, that 1 electron. Lithium is 1s2, 2s1, so 2s1, that's 1 electron, and you can just keep on going. So there's a pattern. These all have 1 valence electron. As I said, in terms of chemical bonding, the number of electrons, valence electrons, is the key. So it's important for us then to recognize these all have the same number of valence electrons. And then you go to the next column where you have beryllium, magnesium, calcium, strontium, and barium. I'm not going to do francium and radium. They all have 2 valence electrons. Okay, you can show that that's the case. Then we come all the way over to the nonmetals and the metalloids. So for example, boron. I'm ignoring the transition metals. We're not even going to discuss them in this context. So if you look at the next column, which is column 3A, 3 valence electrons. And you look at the next one, carbon and silicon, 4 valence electrons. And the next one's nitrogen and phosphorus, 5 valence electrons. And the next one is oxygen and sulfur, 6 valence electrons. And the next one is fluorine and chlorine, 7 valence electrons. And then of course, neon and argon, the noble gases, 8 valence electrons. Okay, helium's a funny thing, right? Helium's a weird thing. It only has 1 shell. So it's, it's in group A, but sometimes people actually move helium over here because it only has 2 electrons, right? So you can extend this and you can say, okay, let's talk, let's put arsenic in here too, and let's put selenium here, and let's do bromine, and let's even do iodine, and let's do krypton and xenon, right? But in any case, the number of valence electrons can be determined just by looking at the position in the periodic table. And that is cool, right? Number of valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. That makes things simple. All you got to do is look at their position, the number of valence electrons without having to do, think about like iodine, right? Iodine's element number 53. 1s2, 2s2, 2p6. Okay, finally you get out there and it's like 5s2, 5p5, which is 7 electrons, and now you have 7. It's just easier just to look at this column. That's 7, right? Okay, so there's our valence electrons. Now, here's what we're going to do. We're going to now introduce what are called Lewis dot symbols. They're cool. So G.N. Lewis was like preparing a general chemistry lecture, so is claimed. And he was looking at these patterns and he came up with this system. Essentially, you represent each valence electron, just the valence, not the core, each valence electron is represented by a dot around the symbol of the element. Okay, so for example, let's take this iodine atom, right? Iodine has 7 valence electrons. You represent those 7 electrons as dots. So in a sense, you're thinking of them as particles, right? They're not, they're waves, but it is useful to think of them as particles in this context. Remember, they are wave particles, right? Electrons are wave particles. So we're not claiming that they are only waves. They manifest themselves as particles and waves. We call that duality, right? So you represent them as dots. So generally what you do is start on the right side and then just go clockwise, 1 dot on each side. 1, 2, 3, 4. Think of corners like a box. And then you start to pair them up. So once you do all 4 sides, you then put a second one until you run out of electrons. And there we have 7 electrons. So that would be called the Lewis dot symbol. This is called the Lewis dot symbol for iodine. Okay, we are representing just the valence electrons. We're ignoring the core electrons. They're in there. They're attracted to the nucleus and they affect the properties of the element, but we're just concerned about the valence electrons for now. Okay, let's do another one. So another one, let's pick one of the alkaline earth metals. So an alkaline earth metal might be strontium. Strontium is element number 38. Okay, well, it's element 38, but how many valence electrons does it have? It's in the second column, group 2A, so it only has 2 valence electrons. So that's pretty easy. 1, 2, right? 2 valence electrons. Okay, so those are called Lewis dot symbols for these elements. Okay, now suppose I needed to do an ion. Let's do, for example, a fluoride ion, F minus. Okay, well, fluorine is in group 7A, so it has 7 valence electrons. So we would write fluorine as 1, 2, 3, 4, 5, 6, 7, but it's fluoride, right? So here's what you do. You put brackets around it to indicate that it is an ion, and then you put the negative there, right? So you move that negative there, okay? So that's just the notation. Then you add an extra electron, right? We got to add one more because it's negative. So where does it go? Well, it's going to go right there, right? And notice you have all these paired electrons. And so that would be the electron, I'm sorry, the Lewis dot symbol for the fluoride ion. So this is for the fluoride ion. It's an anion, right? Okay. Now the electron configuration would be 1s2, 2s2, 2p6, right? That's the electron configuration. But we're only concerned with the valence electrons. So we're just concerned with these 8. These are the valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, right? There's that 8, that octet rule. We're going to talk about that. The octet rule turns out is very important in terms of the stability of atoms, ions, and molecules and everything like that, okay? So far, we're just talking about ionic bonding. Now what we're going to do is let's take a look and find a problem here. So let me get all this out of the way. Okay, drawing Lewis dot diagram. Okay, they call it Lewis dot diagram. It's really a Lewis dot symbol of a main group element or common atomic ion, right? So we did ion. So notice it's main group. Main group are the alkali metals and the alkaline earth metals, group 1A, 2A, and then the non-metals and metalloids. So like group 3A through 8A. Those are called the main group. The transition metals are not part of the main group, okay? Selenium. Okay, we did selenium, so let's look at another one. Aluminum cation, Al+. Now that's actually not a stable form of aluminum, but we can do it anyways, Al+. So aluminum has 13 electrons, but more importantly, it's in group 3A, right? It goes 1A, 2A, then you have the transition metals, and then it's 3A. It's right underneath boron, so it's group 3A. So the aluminum atom would have 3 dots, 3 electrons, 3 valence electrons. But this is Al+, so you're going to lose 1 valence electron. So now you only got 2. So let's take a look. Okay. So aluminum is like over here. It's underneath boron. And so that's in group 3A. Okay, so aluminum. So aluminum has 3 valence electrons, 1, 2, 3. So that would be aluminum. That's the Lewis dot symbol or Lewis dot diagram for aluminum. And then, but we want Al+. So this is Al. We want Al+. Just get rid of one of the dots. That's all you got to do. So you just have Al with 2 dots. And then you do want to put it in brackets and then put your charge up there, right? So make sure you indicate it's just that this is, you know, a charged ion, okay? All ions are charged, right? Okay, so there you go. So that's relatively simple. Okay, so let's talk now about covalent bonding. Okay, covalent bonding, just, you know, real briefly, covalent bonding is the case that it turns out that certain atoms share electrons. Especially nonmetals, but also metals. Okay, so actually there's a type of bonding called metallic bonding. So like all the metals that we work with, aluminum, you know, steel, you know, all those atoms are actually sharing electrons. So if you take a piece of metal, all the atoms in it are actually sharing electrons. It's almost like an ocean of electrons that are moving around. And that's why metals are really good conductors. They're all sharing their electrons in pretty complicated ways that we're not going to go into in this course. But especially nonmetals. So there's also sharing that goes on. And that's the type of bonding we're going to discuss, which is called covalent bonding. So the idea would be essentially like this. If you take a hydrogen atom, the hydrogen atom is in group 1A. It has 1 electron, okay? Now let's take another hydrogen atom. I'll put it over here. And this time I'll draw the dot on the left side, just so it's facing the other hydrogen atom, just so that you can see how that works. It's just easier as a diagram to do this. So notice they each have 1 electron. I'm going to do the following. Underneath them, I'm going to write out the box diagram, right? This is 1s. Okay, so that hydrogen on the left has 1 electron in the 1s orbital, which is the valence shell, right? But it's also, you know, it's the valence shell, but it's also the core, right? So it's both because it's, you know, only 1 there. And the other hydrogen atom, the same thing, right? 1s. And remember, when we only put 1 electron in an orbital, we put it spin up. So something's got to happen here. Essentially what happens is the nucleus for this hydrogen. Now I draw a big H, but remember that big H is really just a proton, right? It's really just a proton. The hydrogen on the right is really just a proton too with an electron, right? What happens is this electron here, if it gets close enough, it's attracted to that proton, right? That proton's positively charged, so it's attracted. And this electron here is attracted to that proton, right? So what happens is this electron is attracted to this one, but it's also attracted to this one, and the other one the same thing. But remember, the electrons repel each other. They're negatively charged, so they don't want to get close to each other. Likewise, the protons are repelling each other. They don't want to get close to each other. But what ends up happening is a really amazing phenomenon, and it's what leads, to life on Earth, which is this idea, essentially, that what happens is when you add everything up, the repulsions and the attractions, the quantum mechanics starts to play a role. And the quantum mechanics essentially says, look, you have this electron in an orbital, and there's only one electron in that orbital, and you've only got one electron in that orbital. Each of those orbitals has space for one more electron. So what can happen is these two orbitals can interact with each other. Remember, they're waves, and those two waves can interact in such a way that you get one orbital out of it, and each of those two electrons can go in with opposite spins. Now, that particular orbital is called a molecular orbital. Remember, these are called atomic orbitals. So each atom has its own atomic orbital. This is called a molecular orbital. Those two orbitals overlap with each other and form a new orbital called a molecular orbital. And remember, an orbital can have up to 2 electrons. Now, one of these is going to have to change its spin, right? Because they can't have the same spin in the same orbital, the Pauli exclusion principle. But essentially what you get now is both of those electrons in the same orbital. And we're going to represent that like this. That's one way to represent it, okay? We now have 2 electrons that are interacting with both atoms, with both nuclei, and we're going to call that a covalent bond. Okay, so it's a quantum mechanical phenomenon, covalent bonding is. It's a quantum mechanical phenomenon in that these waves will interact with each other. They will mix together to form a new type of orbital, which is lower in energy than the atomic orbitals themselves. Essentially, it is lower energy. It is more stable. When we say lower energy, we mean more stable. The lower the energy of something is, the more stable it is. The molecular orbital is lower energy than the atomic orbitals, and so you will end up with what's called a covalent bond. It's a quantum mechanical phenomenon that we really couldn't. We could try to kind of explain it using classical physics, attractions and repulsions and all of that. But the easiest way to describe it is as a quantum mechanical phenomenon, spin up, spin down. And evidence, we can test that, right? We can test the spin and show that they have opposite spins and all of that kind of stuff. So this is what we're going to call a Lewis structure. Not a Lewis dot structure, but a Lewis structure. The Lewis dot symbol or the Lewis dot diagram is what we did earlier. This is called the Lewis structure, okay? Now, it is also more modern to represent it this way. Chemists will use this on the right. So this is also a Lewis structure. They're both Lewis structures, but this is called line notation. Instead of representing these 2 dots, we use a line. So the 2 dots are the line, okay? This is a preferred method. You're gonna see both. Some of the problems at the beginning in ALEX use these dots, and then later on you get to see the line notation. This is the preferred method over here, okay? But you'll see both. So let me show you a problem. Counting bonding and non-bonding electron pairs in. So notice the electrons pair up. Why do they pair up? Spin up, spin down. These atomic orbitals or molecular orbitals have room for 2 electrons, so they tend to form pairs. Pairs are pretty stable in nature. It's a quantum mechanical phenomenon. Below is the Lewis structure for the hydrogen fluoride molecule, HF. Count the number of bonding pairs and the number of lone pairs around the hydrogen atom. Okay, so we're now saying there's 2 different types of pairs. One type of pair is bonding. That's like the ones I just showed you. Then there's non-bonding. So if you look at that structure, I'm going to actually put it up here. And again, chemists really wouldn't draw it this way, but we're at the beginning. what we're going to do is if the pair is in between the atoms, right? It's in between the atoms. We're going to call that a bonding pair. Okay? If it's only on one atom, we call that a non-bonding pair. Or lone pair. Alone, right? That pair is alone. It's only on one atom. So if you're going to count them as they ask you to do, it looks like there's only one bonding pair right there. So the number of bonding pairs is 1. A pair is 2, right? A pair of shoes. And then the lone pair, you would have 1, 2, 3. Relatively simple, okay? Bonding pairs and lone pairs. It ends up being an important aspect of chemical bonding to talk about, to differentiate between these. Now I'm going to draw this in a slightly different way. I'm going to do it this way. Okay, so same thing. This is a bonding pair. And then these are lone pairs. Okay, that's using the line notation. And as I said, be careful. The line notation is what we're going to move into. But at the beginning of the chapter, the problems are going to, use the dots. Okay. There's other systems that people have developed, but that's fine. Okay. Okay. Okay, here's another one. A chemist would never do it this way. But again, we're trying to teach you at the beginning here. Okay. So this is, same kind of problem. So let's count up the bonding pairs and the lone pairs. Okay, so bonding pair, there's one right there. And then there's another one right there, right? So there's 2. There's another bonding pair. It's in between the atoms, right? The pairs in between the atoms. So there's 4. Now that means there's 8 electrons, right? So remember, a bond is 2 electrons. There is such a thing as a 1 electron bond or a 3 electron bond, but we're not going to worry about those. We're just going to count a bond as 2 electrons. So a pair is 2. That's 1 bond. Lone pairs, 1, 2, 3, 4. Remember, the lone pairs are the ones that are only on one atom. If they're in between the atoms, it's a bonding pair. Okay? So, you can go through the arithmetic. How many electrons is it? It's probably 16, right? 2, 4, 6, 8, 10, 12, 14, 16 electrons. Okay? We'll get into the Lewis structures later. Now, the next thing we're going to do is we're going to look at the Octet Rule. Okay? This is a cool problem. Deciding whether a Lewis structure satisfies the Octet Rule. The Octet Rule is 8. That's 9, right? 8. 5 plus 3 is 8. 8 electrons. If the atom has 8 electrons around it, 8 valence electrons around it, it satisfies the Octet Rule, okay? A bonding pair is 2 electrons. A lone pair is 2 electrons, okay? So all you got to do is count up all the electrons around each atom. And let's take a look. So let's do this first one. Here's your proposed Lewis structure. Notice they use the brackets. The brackets are what you put there if you have a charge, okay? We're going to talk later on about how we draw these Lewis structures. Well, we're going to be doing these ourselves, but for right now, they're giving them to you and you want to evaluate. Is this one a reasonable structure? Well, let's take a look. You have a carbon atom. It has 2 electrons there, right? That's 1 pair. Think of it this way. A pair is 2, so you got to have 4 pair. 4 pair would be 8 electrons. So the carbon only has 3 pairs around it, right? 1 lone pair, 2 bonding pairs. So that's only 3 pairs. That's 6 electrons. Nope, it's not a good structure because the carbon atom does not have the correct number of valence electrons. It needs to have 8 valence electrons, okay? Nitrogen's okay, but nitrogen has 2 lone pairs and 2 bonds. So that's 4 pairs, that's 8 electrons. That's okay. The nitrogen is fine. It's the carbon that's an issue there. The problem atom is the carbon here, right? Carbon's a problem atom. Oh, actually, let me be careful here. There's another issue here, which is when they draw these Lewis structures, did they put the correct number of electrons in it? So how do we know whether it has the correct number of electrons? Just do the arithmetic. Carbon is in group 4A, so it has 4 valence electrons. Nitrogen is in group 5A, so it has 5 electrons. 4 plus 5 is 9. It's negatively charged. They're telling us it's negative. That means you add 1 more electron. So that would be 4 plus 5 plus 1, 10. So you got to have that periodic table. Carbon, group 4A, 4. Nitrogen, group 5A, 5. Negatively charged, add 1. If it was negative 2, you would add 2. So that's 10. Let's count up. Do you have 10? 2, 4, 6, 8, 10. So it's not a problem with the number of electrons, valence electrons. Let's do the second one. This one has oxygen, fluorine, and fluorine. Okay, fluorine is in group 7A, 7 valence electrons. There's 2 fluorines, so that's 14. Oxygen is group 6A, so that's 6. So 14 plus 6 is 20. So 1, we have to have 20 valence electrons. So let's count them up. 2, 4, 6, 8, 10, 12, 14, 16. Nope, not enough, right? Not even close. We have to have 20 valence electrons. We've only got 16. So this has the wrong number of valence electrons. Okay, that's the problem there. Let's look at the third one. Carbon, group 4A, that's 4 valence electrons. Chlorine, group 7A, that's 7 valence electrons. Oxygen, 6, right? Group 6A. So 7 plus 4 is 11, plus 7 is 18, plus 6 is 24. Just added up all those valences. So do we have 24? I'm going to start over here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Looks like the correct number of valence electrons, 24. Now we do the octet rule. Chlorine has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. And then chlorine has 2, 4, 6, 8. Okay, so that looks pretty good. Oops. For some reason, the little iPad here got lost. It's connecting now. So we may need to actually just look at the screen here. Okay, so you're looking at 2 things. You're looking at, so everything's good here, right? You're looking at 2 things. You're looking, 1, at the total number of valence electrons. And then 2, you're looking at whether each atom has the octet rule. Okay, so just count up all the electrons around each atom and make sure that it's safe. Notice that like this pair gets counted by both atoms. These 2 pairs get counted by both of these atoms, and this pair here gets counted by both of those atoms there. Okay, I'm sorry, let me stop this. Okay. All right, let's take a look at another one. Oops. I'm sorry, let me just try one more. Yeah, this iPad is acting up today. Okay, so let's take a look at this one. Predicting the single bonded molecular compounds of 2 elements. Okay, so this one, what they do is they give you 2 elements and they want you to know what they want you to figure out what the chemical formula is going to be. Okay, so here's what you can do. You can assume everything's a single bond and not a double or triple bond. So we'll get into double and triple bonds later on. But what you do is you essentially say, look, hydrogen has 1 valence electron and fluorine has 7. So how many more electrons does fluorine need to get up to 8? It needs 1 more electron. So it will form 1 bond with the hydrogen. So you would end up with 1 hydrogen and 1 fluorine, and that would give you the structure there, okay? So let's try, so the chemical formula then would just be HF. The name is easy, you just call it hydrogen fluoride, right? The fluoride is the negative, so non-metal. Now what about sulfur and chlorine? Which element pair? So same thing, what you do is you say, okay, sulfur is in group 6A. So sulfur is in group 6A, so it needs 2 electrons. Chlorine is in group 7A, so it only needs 1 electron, right? If you're in group 7A, you just need 1 electron to get up to 8. So the chlorine is going to form a bond to the sulfur. By forming a bond, it gets 1 more electron. So the chlorine only needs 1 sulfur. But the sulfur needs 2 chlorines because the sulfur has 6 valence electrons. So it needs 2 chlorines to get up to 8. I'm sorry. Looks like we're crashing here. Okay. So what will happen then is you'll end up with the sulfur forming a bond to 2 chlorines and the chlorine forming a bond to 1 sulfur. Okay. So I'm going to end it right there. Oops. So I'm going to end it right there because I'm having some technical issues, and we'll pick this up. We'll pick this up on Monday, and we'll continue looking at these Lewis structures, and then we'll start learning how to build these Lewis structures, and then we'll do all these sort of tests for Lewis structures. So reach out to me if you have any questions, and have a great day. And if I don't hear from you, have a great weekend as well. Okay, take care.